Hello dear colleagues, my name is Bakurov. I am going to present you my abstract called Calculation of the transmission of a structure based on a tapered optical fiber insertion. Active studies of fiber structures with insertions of non-standard fibers are due to the possibility of their use as sensors that measure the parameters of the external environment. The sensitivity of structures with insertions increases significantly if an interferometer is made, which couples different fiber modes. The amplitude of the interference signal depends on the amount of light intensity coupled to the cladding mode by the insertion. The insertion length must be selected in such a way that the intensity remaining in the core should be at the level of the amplitude of one of the excited cladding modes, that is 20 to 50%. The required length of the insertion depends on the type of special fiber used and lies in the range from 0.1 mm to a few millimeters. In addition, after splicing the structure and measuring its transmission, the insertion length can be adjusted to obtain the required values. In this case, it's necessary to create the structure with the insertion again. So, we propose a method for adjusting mode coupling in the fiber by increasing the length of the insertion heated and stretched it in electric arc discharges, that is tapering the fiber. We tapered fiber by welding machine for fiber splicing that you can see at the first figure. Also, you can see the model of the tapered structure at the second figure and photos of the tapered structure at the third figure. Such tapered structures can be used in measuring of parameters of external environment. Also, these structures can be used as an active medium for high-power fiber lasers and amplifiers and for controlling of spectrum width. To calculate the field at the output of the structure, we found the values of the effective refractive indices of all modes of the fiber of the insertion. To calculate the values of the effective refractive indices of the tapered fiber, it was assumed that the change in the fiber radius occurs according to the Casein Law. The electromagnetic wave enters the insertion from the standard fiber, so we decompose the field of the core mode of standard fiber into modes of the insertion fiber using Formula 1. Coupling coefficients can be obtained by Formula 2. The phase change can be calculated using the third formula. The sum of the fields multiplied by the coupling coefficients gives the field transmitted through the insertion. And the final transmission coefficient can be obtained through the overlap integral over the fiber cross-section between the field in the insertion and the standard fiber core mode field. Doing this calculation for every length of insertion, we can obtain dependence of the transmission coefficient on the length of the fiber insertion. To begin with, an experiment was carried out to determine the dependence of the insertion radius on the number of discharges for the SM600 fiber. Using this dependence when calculating the transmission of the taper, it's possible to obtain more realistic values of the transmission coefficient. The experiment used an arc time of 180 milliseconds. The relationship is shown in Figure 7. The experimental results were approximated by a polynomial of the second degree. Based on the approximation, it was assumed that in 30 discharges, the insert radius decreased from 62.5 micrometers to about 21.5 micrometers. To test the theoretical results, two experiments were carried out with the SM600 fiber. In the first experiment, an insertion with a length of 160 micrometers was made. In the second experiment, an insertion with a length of 200 micrometers was made. 30 electric arc discharges were applied to the insertion. From figure 8, it can be observed that the behavior of the theoretical and experimental curves is similar. This shows that the theoretical model corresponds to a real experiment. The difference in transmittances of 5 to 20% between theory and experiment can be caused by splice losses. The proposed method for taping a fiber insert can control the mode conversion coefficient. Simulations have shown that changing the fiber diameter from 62.5 to 30 micrometers can reduce the transmittance to the core mode from 60% to 20%, thereby increasing the fraction of the energy propagating through the cladding by 40%, which can then be used to obtain intermode interference. Good agreement is observed between the experimental and theoretical results. Numerical modeling can be used to find the optimal fiber tapering parameters and obtain the required transmittance of the fiber insertion. Thank you for your attention.